Hi, welcome to es201 Computer Techniques. This is week 6, class 2, and the topic today is recursive functions. So here are the objectives of this class. First, I'm going to spend the first half of this explaining this week's homework assignment, primarily focusing on the second program, which is in chapter 7, called Program 6.2. Then we will go ahead and we'll define what is meant by a recursive function, and then we'll go through a couple examples to make sure we understand how a recursive function operates. So first I want to explain the homework. This is actually hopefully a pretty fun homework to do. I think it's pretty fun. It involves writing a recursive function, but it's got some background in terms of Bitcoin. And I will be explaining that here in the next few slides. So first, what you're going to do in your program is you're going to write a recursive function. And what that's going to do is it's going to create a Merkle tree of hash functions. And I'm going to define what is a Merkle tree and what is meant by a hash here. Then your program is going to hash the lines of a text file that I've provided on Blackboard. It's called transactions.txt, and you're going to go ahead and process that. And in the end, you're going to end up with a single hash as a result of the Merkle tree. And then the last thing I want to mention is that as extra credit, you can mine for the lowest hash, and I'll explain what this is. This is extra credit, and the person with the lowest hash value at the end of this competition will get actually 3 extra percentage points on their course grade. So a pretty good reward. Hopefully that entices you to go ahead and participate in this competition. All right, so first I want to go ahead and explain what is Bitcoin, if you're not familiar with Bitcoin. And Bitcoin is what's known as a virtual decentralized cryptocurrency. And what I'll go through and define what each one of these terms are. Virtual is a type of unregulated digital money which is issued and usually controlled by its developers and used and accepted among the members of a specific virtual community. This is the definition from the ECB, which is the European Central Bank, and it's pretty good. So the key here is that there's no physical quantity. It completely exists in digital form. Decentralized means that there's no controlling power, and it essentially exists by agreement of majority consensus. So if you think about the United States, the Fed controls the dollars. In Europe, the ECB controls the euro. There is no one that controls a decentralized currency. And a cryptocurrency is a medium of exchange that uses cryptography to secure transactions and maintain anonymity or pseudo-anonymity. Just kind of a little bit of background. This was actually created back in 2008 by a person called Satoshi Nakamoto. They wrote an online open source paper, and just kind of an interesting thing about this Satoshi Nakamoto, no one has ever stepped forward to claim that they are that person. So we don't actually know if that person exists, if it's a group of people, or what. It's just online someone posted under that name. And then this was put into some open source software that started out in 2009. So it's kind of like the birth of Bitcoin. So this is kind of interesting. This is actually the price of Bitcoin. If you're watching it in the news, it's incredibly volatile. So if you look, the current price as of yesterday was about over $4,300 per Bitcoin. And if you look, this was just like a year ago, it was less than $1,000. So this is actually increased a lot, and then the volatility of it is exceedingly large. And so there's been some questions by investors of how long that can be maintained. I want to explain the blockchain. This is kind of a principle behind Bitcoin, but blockchain can be used for things other than Bitcoin. So a Bitcoin is a public append-only ledger. It records every transaction that was ever made. So let's talk what we mean by that. Essentially, if every time somebody paid somebody else, that was considered a transaction, and we can kind of think of that as these little blocks, individual blocks here. If you were to go ahead and just write those into a ledger, but a ledger that you can never erase, it would just kind of keep building longer and longer and longer. And that's kind of the idea of a read-only ledger. And then in Bitcoin, the proof of ownership is verified by essentially going back through that ledger and making sure that everyone that claims they have Bitcoins indeed did. So let me go through an example. Let's say that Alice wants to give Bob 2 Bitcoin. Now, in order to go ahead and determine whether that was true, since we don't have any physical Bitcoin that Alice can actually hold in her hand and say, here are my 2 Bitcoin, what we have to do is we have to go through the ledger and find some point where Carl gave Alice some Bitcoin. And if we were able to read back far enough, we see that Carl gave Alice 5 Bitcoin, we'd realize that she actually had the 5 Bitcoin that she could give. But we have to kind of continue to read back and find out, make sure Carl had those 5 Bitcoin that he could have given Alice. So we go back and read, and maybe we see a couple more of these transactions. So this right over here is a transaction, this is a transaction, this is one, and these are all these individual transactions that are occurring in the blockchain. And this just goes back and back and back until the very, very beginning, and then you can verify that all those people that claim they had Bitcoins indeed had it. We're going to look at how computers can do this very efficiently. You can imagine if you're a person reading a giant ledger like this with hundreds of thousands or millions of transactions, it would be very difficult to do. In order to do that, we have to introduce the concept of a cryptographic hash function. And hash functions in general take some arbitrary sized input and turn it into a fixed sized output. And in order for that hash function to be cryptographic, it means it needs to be impossible to invert, which means go in the reverse direction. So here I'm just going to show you, this would be an example of 3 hashes. And so I'm just taking some input here and converting into this output here. And those happen to be the same size, same number of bits. But hash functions always generate the same size, so essentially the same number of bits on the right-hand side. So if I was to hash a small input, I would have some hash that would be of the same size as any other hash. A very, very large input, I'm always going to get the end. So hash functions always generate output of the same size. They're going to have different bits in there, different zeros and ones, but they'll always be the same number of bits. So kind of pictorially, this might be a little bit easier to see. Here I have various inputs that are just text strings, a bunch of words. It's going to go into some hash function. And then what's shown over here on the right is actually the hash. And if you see, those are all the exact same size. They're all shown as hexadecimal values. And so, but each one of those is of the same size. Now, if it was to be cryptographic, it means that you can't actually look at this and be able to go back and find out that that said Fox. But it's really easy to say, hey, Fox actually turns into that digest. So let's say this hash function is also what we talked about earlier as a trapdoor function. So let me talk about cryptographic hash functions, and that means that it's non-invertible. And what that means is that no 2 text strings can produce the same hash. And one way to think of it is, over in this blue box, if this was every possible text string you could ever imagine, which you can imagine every possible sentence would be incredibly huge, because those sentences can be all lengths that you want, from 2 letters maybe all the way up to hundreds of thousands of letters. But if you look at all the possible hashes that are always of the same size, there's actually a fixed number that you can have in there. So this green box is smaller. So hashes are, in theory, you can always find, there could always be 2 in here, but the question is whether you could actually find them in a finite amount of time. If you found 2, that would be called a collision. And that means you identified 2 little locations in this blue box that produce something in the same green box. So the question is, how big does my hashes need to be? And so here I show the current hash. This over here is a 32-bit hash. And so a 32-bit hash is going to, or sorry, 32-byte hash is going to have 256 bits. And so 2 to the 256 is 1.158 times 10 to the 77. So that's the number of possible different hashes. That's the number of possible spots there are in that green block. So now imagine trying to find 2 things in the blue that are going to end up giving me the same hash. And to kind of put this in scale, if you look at the number of seconds since the Big Bang, that's only 4 times 10 to the 17th, much, much smaller. If you look at all the grains of sand on Earth, that's only 10 to the 21, so clearly that's much smaller. If I take the world's fastest computer, which is the Tiani 2, and look at how many operations it would have performed if it existed from year 0 AD to now, that would still only be about 2 times 10 to the 27th, which is still way, way smaller. So clearly, this is a huge number. And in fact, the only number that even kind of comes close to that would be, if you look at all the atoms in the universe, that's estimated about 10 to the 80. So that's all the number different possibilities you can have of just this simple, right over here, 32-byte hash. So let me talk about blockchains and hashes and how they fit into Bitcoin. Hashing simplifies is verifying that blockchain, because now what we're going to do is we're going to take that entire ledger and hash it into one simple, relatively simple looking 32-byte string. So here you have all your transactions and you turn them into a hash. So this is the way Bitcoin works. It takes all these transactions, shown as the purple ones, and bundles them together, just kind of puts one after the other, and then it goes ahead and hashes that entire thing and generates this single hash right there. And then you take another bunch of transactions that happen the next day, and you go ahead and take that input and the hash from the previous day and create a new one. And since each one of those hashes is going to be unique, there's no collisions on it, effectively everything that's ever happened within this, all those transactions previously is always stored in just that single little hash there. So it's a pretty unique way to go ahead and verify transactions simply by looking at what that hash is. Now, the way that those transactions are bundled together, the purple ones turn into that, is done. This is just a practical issue to go ahead and do that in a Merkle tree. And a Merkle tree takes each transaction, so that's what's shown down here is the L's, and it goes ahead and each time it takes a transaction and then hashes it, and then it'll take two right next to each other, concatenate them together and hash that, and then take two next to each other, concatenate them, hash that until you end up with one single 32-byte hash at the top, and that right there is called the Merkle root. I realize it's at the top, but you could also draw this inverted, which would make it seem clearly that it's a Merkle root, but it's going in that direction there. So that would be, this is called a Merkle tree. So this is what you're going to be doing in the homework. I give you a list of what I call transactions, or actually quotes. It's a text file called transactions.txt. It's on Blackboard. And what you're going to do is your program is going to read in that text file and store that in a vector. And actually, you don't need to worry that about that part of the code. I've actually already written it. It's in the template called main.cpp that's on the website. And then what you'll do, if there happens to be an odd number in there, you will duplicate the last number, so you always end up with an even number of transactions that you have. Then what you'll do is you'll hash each line of the text, and you're going to use the SHA-256 library, which I'll mention a little bit more here in a minute. The code for that is on Blackboard already, so you don't need that. Then you will go ahead and concatenate two hashes together, and then go ahead and hash that concatenation and continue until you only have one hash left. Your vector only has one element in it, and that is what's known as the Merkle root. So here you kind of, again, pictorially show where each one of these now is going to be lines of the text file. You're going to go ahead and hash and then put them together, concatenate, hash, etc. up. And so you're going to end up with a single function. Just kind of, this is fairly straightforward if you think of using strings and vectors that we've already looked at. If you want to concatenate two strings together, you simply use a statement like this. You've got two strings, 1 and 2. You just say str3 is 1 and 2. That concatenates together. And then in order to create the hash, there's a library that does this for us. It's called SHA-256. That's on the website. All you need to do is include the header file, just like we did when we were using the ping library. So you're going to put this in there, and that's actually already in the template file that I provided with you. And then the function name is called SHA-256. You send it the string you want to hash, you get back a string. So pretty straightforward, pretty easy to do. And that's the only function you need to do. And you'll just compile all those files together, just like you did in the lab with the ping library. So here's the main program that I provide. It's on the website as well as listed in the Zybook. And so here, just some include statements that you need. And the main function is fairly small. It starts here and it ends right there. What your job is to do is you're going to be adding a function down here at the bottom. The function that you're creating is the one I show the prototype right here. The functions you're going to make is called Merkle. And it's going to take a vector of strings and it's going to return a single string. So what it's doing is all those strings, that's a vector of all those quotes in the file, and this comes back is going to be the single hash, which is the Merkle root. So you've actually gone through and processed all of those transactions and concatenated and all the way up to the top. And so that's going to be your recursive function. So you'll put that down at the bottom, and the main program just goes ahead and outputs that your program is functioning properly. So the way that this works in Bitcoin, which is kind of interesting, is that in order for people to verify all those transactions, a reward is given to them, and the current reward is 12.5 Bitcoins, which is, if you look at that, current price is over $50,000. So there's actually clearly incentive to go ahead and operate in the Bitcoin mining community. And then since there's lots of people doing this, essentially the consensus of the majority says, yeah, those are the right transactions in order to do it. Now, in order to give this incentive, these 12.5 Bitcoins, these are actually created. That's where the term mining comes from, more or less created out of nothing. So what you do if you're a miner is you take all your transactions, which are the purple blocks there, you add a transaction at the bottom that says, hey, and that's supposed to create 12.5 new ones and give them to me, and then you go ahead and create the hash, and then you want to go ahead and get that onto the blockchain. Now, since people are competing to do this, to determine whose transaction that says give me 12 Bitcoins applies to it, you also then apply what's called a nonce, which is yet one more number that you need to hash in here, and then your resulting hash has to have a very, very low value. So the idea is that you're going to take what would be called the Merkle root, you add this nonce, you create a hash, and then everyone's trying to find some hash that has some very, very low values. So maybe you go on and on and on until somebody gets one that is less than, say, 3 zeros right there, and that would be like the winning one. And so there's a goal, and everyone keeps working until they get it. And that is set such that a group of transactions, on average, gets found about every 10 minutes. And what happens is we just keep making the problem harder and harder as computers get faster and faster. So this is just sort of in the specifications of the way Bitcoin operates. Since this is very popular, what's happened is lots of people have created huge banks of computers. This is a picture from China, and these is just racks and racks and racks in a giant factory of computers that are all trying to do this mining. And the reason is, as you saw, every 10 minutes someone's getting paid over $50,000 to go ahead and verify transactions. The number of Bitcoins in circulation, since they're being created, is increasing with time. Right now there's over 14 million Bitcoins in circulation. So the total value of Bitcoin is incredibly hard if you take 14 million and then multiply that by your over $4,000 per Bitcoin that you have. The number of transactions is also increasing exponentially as more and more people are using the Bitcoin network. So here's the mining competition. This is the extra credit. Everyone needs to write the recursive function, but once you've done that, you might as well compete in the competition and see if you can get those 3 percentage points. So what you'll do is you'll just use your program, but you will then go ahead and append a personal statement line to your file, just like you would kind of do in Bitcoin. That sentence that you're going to add to that file says the 3% reward shall be paid to, and then make sure you put your name in there. And that's going to be line 9, because there's 8 lines in the text file. And then you're going to append another line. This is going to be functioning as our nonce of real text, any sort of text that you want. Can't be random characters, but like some words in there. And then what we're going to do is find out who can find the smallest value, the lowest value hash of those 10 lines of text. So you're going to be essentially getting a Merkle root of now 10 lines of text for the competition. You did the first 8 are the ones you used for your homework, and then you just added these 2 lines of text. Your 9th line will always be the same per person. You'll always have that line, but you're always going to be guessing new lines of text to do as your 10th line and trying to get a really, really low value. So the lowest hash value is going to win. Lowest meaning the most zeros at the beginning of it. So, for example, this shows a fairly low hash. We've got all these numbers of zeros. So you'll just go ahead and keep finding it, keep guessing real lines of text to go ahead and stick in there until you find a really low hash value. To keep track of this, there's a discussion board on Blackboard, and you can go ahead and post your results in there. So just again, to kind of show you what this will look like, you're going to have this text file. I'm showing the end of the text file here. These are line numbers. They're not actually in the file, just to kind of help you see. There's 8 quotes in there. So there you see on line 8 is the 8th quote. On line 9, I've added my payment line, and you can see where I have those words. And then what you're going to do is then you're going to add a 10th line, which is any line of text that you want. And this is what you're going to keep changing in order to get really low hash value. So maybe I added this as my 10th line as my line of text. And then I go ahead and hash and create the Merkle root of those 10 lines of text. I use my program that did it. And then I'm going to go ahead and find one. And actually, I've already posted in there just to start off the competition. This is my line of text. She will be taken good care of. That results in the hash I show here, which has 3 zeros at the beginning, and there's my name. Anyone can go and verify that this is correct, because you will just take your 8 lines of text, put that the 3% will be paid to, and you see my name here, and then you'll go ahead and add this line of text at the end and verify it. So it'll be very easy for everyone in class to go ahead and verify somebody else's transaction. And since all of our line 9s are going to be different, they're all going to have our name on it, we're all kind of trying to get a low hash, but we're all working with a different set of text. So you can't actually we're not all working on the exact same problem. So, all right. So that's it. Background on the homework. Let me just kind of quickly review what is a recursive function. And recursive function is just a function that calls itself. So let me show you what that means. Here I have a function called func. It's recursive, and that means that within the function itself, I have some line that calls itself here. So you can see inside this function, because here are the curly brackets, it's actually calling itself. And so what it's going to do is it's going to pause at this point, create a new copy of itself, and go ahead and operate again. And there are some problems that are best solved by just breaking this into smaller ones, because you're repetitively doing the same thing. And the Merkle tree is exactly one of those. And so any type of fractal picture you can imagine is. And so if you want to go ahead and create this thing over on the left-hand side, I just kind of keep breaking that down into smaller and smaller pieces until I have the very, very smallest piece, and then I just go ahead and roll those all back to end up with the original one. So it's kind of in the mechanics. Recursive functions usually have an if-else structure to them. So let me show you. Here would be an example to help illustrate how this is going to work, so you can kind of start to get your head around this. Here's my function called func1. It's a recursive function. I have an if-else statement in it, and I'm just kind of showing some key parts to this so we can focus on it. And within the if start statement, it is calling itself func1 right over here with this parameter a. And so what's going to happen is when you call this function, say that this condition is true, so it goes into the if part. Maybe it does some stuff that changes the value of a. Then it goes ahead and calls itself with that value a. What it does is it's going to create another copy of itself, and it's going to then pause this part, go over to this new copy of func1 using the value that was sent it, and continue to operate through. Now maybe the condition is still true even in the second case, so once now I'm going to go ahead and create a third copy of itself and then continue to operate, and both of those first two functions are paused. So now let's imagine that at this point a has been modified such that now it doesn't go into the if part, it goes into the else. At that point we now come over here to there where it says return, and now what we're going to do is we're going to return back to the calling function. We're going to now unroll ourselves. So now I'm going to come back over here. I just finished that function that it called, so I'm going to return right here. Since I did the if statement, I'm not doing the else in this function. I'm now going to come down over here, and now I'm going to go ahead and return at that point and going back to the next one up. And this is how the functions unroll. So essentially it follows all the ifs on the way down, and then all the once you hit an else, it's going to go ahead and return on the way back. And so this amount of recursion can happen many, many times. Okay, so let's go ahead and just kind of practice it. I've got a couple examples here which will help you kind of figure it out. And so what I'd like you to do is pause this, because you'll need to think about this for a little bit. But here I have a recursive function up at the top, and then I have a main, and I want to know what's the value that's going to go into the variable out. So again, I encourage you, pause the video, step through this, and then see if you can come up with the right answer. Okay. Well, the correct answer to this is B, which is the value 1. And the reason it was is, if you looked at what happened, hopefully you saw this, 10 went into here. Every time V1 was greater than 5, it did the if statement. The if statement decremented V1, and then it would go and call itself again. So this number is going in, it's going to be 10, 9, 8, 7, 6, 5. And then once it's 5, V1, once 5 is not going to be greater than 5, then it goes into the else statement, which says return 1. So now return 1 gets over there, going the next one up. Now we have V1 being 1, and then it's going to go ahead and return that value to the next one up, and it keeps handing that value of 1 all the way to the end. So the value there is 1. All right, we're going to go through a couple more examples here, and so I really encourage you to, again, to pause and think your way through this. I'm just going to make some small modifications to this program we just went through. So what I've done is I've returned I've removed one statement there that I'm showing in that gray block. Everything else is the same. So now I want you to figure out what would be the returned value at the end. Okay, well now the answer is going to be 0. And the reason it's going to be 0 is when the system unrolls, right, it unrolls when it was returning that value of 1. It came up here, and then what it did is it went down, because there wasn't a return statement here. It goes down to this main function's returning 0, and now it starts handing 0 all the way back up. So it handed 1 the first time, and then on the returns, every other function returned to 0. Okay, so now I'm going back to the original one, but now what I've done is I've changed the return function, the return value in the else statement. Okay, well, the correct answer to this now is going to be 5. So remember, the first time it gets into the return statement was when we had is 5 greater than 5, and it wasn't. So it went down here and returned 5. 5 went back up to the one above it, which also said return 5. Returned 5, and it handed the value 5 all the way back up to the top. All right, one last one. And so this will, if you can get this one as well, then you should be in a good way. What I've done is I've removed that statement right there in the gray block. All right. Well, the correct answer to this is F. This is actually be an infinite loop. What I removed was that where I was taking V1 and subtracting 1 from itself. So I was saying V1 is V1 minus 1. So now V1 never changes. So what happens is the value 10 goes in here, and then it calls itself with 10, and it stays 10, and it stays 10 forever. So you need to be careful. You can essentially create infinite loops. It's going to do this until it runs out of memory, because it's creating a new copy of that function each time and sticking them on a stack, just like a stack of plates, and at some point it just runs out of space. Okay, that's it. Next week we're going to start looking at objects and object-oriented programming. See you then.